everyone. I welcome you all to this digital classroom for the subject control systems. In the previous lecture, we solved few problems related to the construction of root locus. Today, let us solve few more example problems related to the construction of root locus. You can take down this question. Sketch the complete root locus of system having g of s is equal to k into s plus 1 divided by s plus 2 into s plus 3 into s plus 4. Let us solve this problem. We know that the root locus is a graphical representation in S domain and it is symmetrical about the real axis. Let us construct the root locus following the steps. Step 1. The given open loop transfer function in this example has 3 poles and 1 0. So, therefore, the number of poles P equals to 3 and the number of zeros Z is equal to 1. And the number of root locus branches is equal to the number of poles of the open loop transfer function. That is, as P greater than Z, N will be equal to P. N represents the number of root locus branches. And out of these N branches, P of the branches which is emerging from open loop pole will be terminating at Z zeros. As we have Z is equal to 1, out of the 3 branches from the pole, one of the branch will be terminating at a 0 and the remaining P minus Z branches, that is 3 minus 1, that is 2 branches, will be terminating to infinity. Therefore, at k is equal to 0, the starting point will be at the poles, and when k reaches infinite, the terminating point will be at zeros. Therefore, at k is equal to 0, we have the starting point at minus 2, that is the roots of the denominator polynomial from the given open loop transfer function. As we have 3 poles, we get the location of pole at s plus 2 is equal to 0, that is s is equal to minus 2. Then s plus 3 equal to 0. We have a pole at s is equal to minus 3. Then equating s plus 4 equal to 0, we get the location of the pole at minus 4. And the terminating point, that is at k is equal to infinity. Just look into the numerator polynomial. The roots of the numerator polynomial of the given open loop transfer function s plus 1 equals to 0. Therefore, we have a 0 at the location s is equal to minus 1. And rest of the P minus Z branches, as I told you just now, that is 2 of the branches which is emerging from the pole minus 3 and minus 4 will be terminating to infinity. Now let us mark the location of poles and zeros in the S-plane. We have a pole at S is equal to minus 2 and at S is equal to minus 3 and a pole at S is equal to minus 4. And also we have a 0 at S is equal to minus 1. Poles are represented by a cross mark and zeros are represented by a small circle. Let us move on to step number 2. Step number 2 is to find the region of root locus, that is the existence of root locus. You know the procedure. Let us take a point on the real axis somewhere here or somewhere here and look towards the right side and ask the question whether you could able to see any odd number of poles and zeros towards your right. We don't have any poles and zeros towards the right of the point which I have chosen. Therefore, root locus does not exist in this region. I can write it as NRL. Now let me take a point here. Look towards the right and you can ask the same question. Can you able to see any odd number of poles and zeros towards your right? In this case, I have 1 0, which is an odd number. Therefore, a root locus exists towards the left of an odd number of poles and zeros. So, root locus exists in this region and I can write it as RL. Now, let me take a point here and let me look into the right side. In this case, I could able to see the number of poles and zeros towards the right is 1 pole and 1 0. So, the sum is 2. Therefore, root locus does not exist in this region towards the left of an even number of poles and zeros. Root locus does not exist. I can write it as NRL. Now let me take a location here, some point I have chosen here in this region. Look towards your right side. In this example, I could able to see 1, 2, 3, a total of 3. That is odd number of poles and zeros towards the right. Therefore, I can see that root locus exists towards the left of an odd number of poles and zeros. And I can write it as RL. Now let me choose a point here. Look towards the right and I can make the count as 1, 2, 3 and 4. Therefore, root locus does not exist towards the left of an even number of poles and zeros. So I can write here as NRL. Making use of step 2, we have marked the existence of root locus. Therefore, root locus exists between -2 and -1 as well as between -4 and -3. And also making use of this step, we could able to predict the existence of breakaway point. We know the procedure to determine the presence of a breakaway point. If we have any two adjacently placed poles or adjacently placed zeros, and if it is in the region of root locus, then there exists minimum one breakaway point if it is an adjacent poles, and there exists minimum one breaking point if it is an adjacently placed zeros. Let us check for these cases here. In this case, we could able to see adjacently placed poles at -4, -3 and -3, -2. Out of these two cases, -3, -2 is not in the region of root locus. Therefore, I cannot take this into consideration. Only possibility is within the region -4 to -3. And these two adjacently placed poles are in the region of root locus. Therefore, there exists minimum one breakaway point in this region. So we have predicted in this case that there exists a minimum one breakaway point between -4 and -3. Let us justify this in the coming steps. Moving on to step 3 and 4, we have to determine the value of centroid and the angle of asymptotes using the formula. To calculate the asymptotes, we have the formula theta equal to 2q plus 1 into 180 degree divided by p minus z, where q ranges from 0 to p minus z minus 1. In this case, number of poles is 3 and number of zeros is 1, and we have -1 here. Therefore, the range of q will be towards 3 minus 1 minus 1, that is 3 minus 2, that is 1. So the range of q is from 0 to 1, that has been specified here. When substituting for q is equal to 0 in this expression, theta will be equal to 180 degree divided by 3 minus 1. That is 180 degree divided by 2. Therefore, theta 1 will be equal to 90 degree. Substituting for q equal to 1, theta 2 will be equal to 2 plus 1, 3 into 180 degree divided by 2. Therefore, theta 2 will be equal to 270 degree. Making use of step number 4, let us calculate the centroid, which is given by summation of real part of open loop poles minus summation of real part of open loop zeros divided by P minus Z. The real part of open loop poles are minus 2, minus 3, minus 4. And as it is summation, let us sum up all minus 2, minus 3, minus 4. Minus of the real part of zeros in this example, we have minus 1. Therefore, minus of summation of real part of open loop zeros, that is minus 1. The whole divided by P minus Z. P is 3 and Z is 1 in this case, therefore divided by 2. Minus 9 plus 1 divided by 2, which is equal to minus 8 divided by 2. Therefore, the centroid will be equal to minus 4. Let us mark the centroid at sigma equals to minus 4, and with centroid as center, let us plot the asymptotes at an angle of 90 degree and 270 degree. Let me make use of the protractor. Have the centroid as the center of the protractor and mark an angle of 90 degree for the first asymptote theta 1 exactly at 90 degree. I have marked with the first asymptote. Tilt the protractor and let us mark for 270 degree. This angle is 180 degree, 190, 200, 210, 20, 30, 40, 250, 260, 270. Exactly. This region is 270 degree. Let us mark for 270 degree. Let me take the ruler. Having centroid at sigma is equal to minus 4 as center, let us mark for both the asymptotes at 90 degree as well as at 270 degree. I mark for 90 degree and similarly represent for the second asymptote theta 2 exactly at 270 degree in dotted lines. From the centroid at sigma is equal to minus 4 as reference, we have an angle exactly at 90 degree, the angle of the first asymptote exactly at 90 degree, and the angle of the second asymptote exactly at 270 degree. Therefore, let us mark the asymptotes here exactly at 90 degree and at 270 degree with centroid sigma at minus 4 as reference. We have done with step 3 and step 4. Let us move on to the next step. Step 5 is to determine the breakaway point. Making use of step 2, we have found that there exists minimum one breakaway point on the real axis between the poles minus 3 and minus 4. By using the following procedure, let us find the location of the breakaway point. The first step is to write the characteristic equation 1 plus g of s into h of s equal to 0. The open loop transfer function g of s with unity feedback is given by k into s plus 1 divided by s plus 2 into s plus 3 into s plus 4. So let us simplify this characteristic equation. Once after simplification, I get the characteristic equation as s plus 2 into s plus 3 into s plus 4 plus k into s plus 1, which is equal to 0. Now from this expression, we have to write k in terms of the polynomial. Therefore, taking the first term towards the right side and taking the coefficient of k, that is s plus 1, towards the denominator, we get k is equal to minus of s plus 2 into s plus 3 into s plus 4 divided by s plus 1. For the simplification, I get minus s cubed minus 9s square minus 26s minus 24 divided by s plus 1. Once after determining k in terms of the polynomial s, now we have to differentiate k with respect to s, that is dk by ds. We have to find dk by ds. This is of the form u by v. Therefore, we know the formula v du minus u dv divided by v square. We have v as s plus 1. Therefore, in the denominator, we get s plus 1 the whole square. And in the numerator, we have to use this formula v du. So, s plus 1, that is v du. You have to differentiate the numerator term. Differentiation of minus s cube is minus 3s square. Differentiation of minus 9s square is minus 18s. Differentiation of minus 26s is minus 26. And differentiation of a constant 24 will be equal to 0. Then let us continue with the formula. Minus of u. U is nothing but the numerator term. I have completely written the numerator term here. Into dv. I have to differentiate the denominator s plus 1. Differentiation of s is 1 and a constant plus 1 is 0. And we have to equate dk by ds equal to 0. Taking s plus 1 the whole square towards the right hand side, it becomes 0. Therefore, for the simplification, I get the expression as minus 3s square minus 3s square minus 18 square minus 18 is minus 26s minus 26 plus s cube plus 9 square plus 26s plus 24 equal to 0. For the simplification, you get the expression as 2s cube plus 12s square plus 18s plus 2 equal to 0. Therefore, the highest power is 3 here. Therefore, you get 3 roots after simplification. At the locations, s is equal to minus 0.12, minus 3.532, minus 2.3472. We have 3 breakaway points at the 3 locations. Now, out of these 3 breakaway points, which one of the breakaway point is going to be valid? Let us check for it. These are the locations of the poles and the zeros and the existence of root locus, as well as the centroid and the asymptotes at 90 degree as well as at 270 degree. And if you mark the first breakaway point, it is exactly at minus 0.12, which comes somewhere here in this location. And this is not a valid breakaway point as it is not in the region of root locus. As well as it's not satisfying the condition that it is not between any two adjacently placed poles. Therefore, it is not valid. And the next case, we have a breakaway point at minus 3.532, which is exactly located here. And this justifies the statement that we have two adjacently placed poles. And it is in the region of root locus also. Therefore, this breakaway point is a valid one. Whereas for the third case, at s is equal to minus 2.3472, it lies somewhere here, and this is an adjacently placed pole, but it is not in the region of root locus. Therefore, the third case is also not valid. Hence, it is very clear that there exists minimum one breakaway point in this region, and its location is exactly at minus 3.532. Moving on to the next step. Step 6 is subjected to the calculation of intersection of the roots on the imaginary axis. We have to find out whether the root locus is intersecting on the imaginary axis, and if it is intersecting on the imaginary axis, exactly at which location does it intersect. Let us follow the procedure. We know the procedure to calculate the intersection point. That is, first we have to write the characteristic equation. We have found the characteristic equation already with respect to the previous step 5. That is s cube plus 9s square plus s into 26 plus k plus 24 plus k, which is equal to 0. Once after writing the characteristic equation, the next step is to generate the root array. Let us generate the root array, taking the coefficient of s cube, s square, s to the power 1, as well as s to the power 0. The first two rows, you know to fill up the first two rows. Taking the coefficient of s cube as 1, immediately below that you can write the coefficient of s square as 9. Then the s coefficient is 26 plus k and the constant 24 plus k. Once after filling up the first two rows, to fill up the third row first element, we know the formula 9 into 26 plus k minus of 1 into 24 plus k divided by 9. Therefore, I can write it as 9 into 26 plus k minus of 24 plus k divided by 9. And the third row second element will be equal to 0. For the last row, that is s to the power 0 row, we know the formula. The first element of s to the power 1 multiplied by 24 plus k minus of 9 into 0 divided by again the same element. As we have the same element in the numerator and denominator, it can cancel out. Therefore, the first element of s to the power 0 row will be 24 plus k. Let me simplify this expression. 9 into 26 will be 234 plus 9k minus 24 minus k divided by 9 greater than 0 is a condition for stability. 9k minus 9 will be 8k and 234 minus 24 will be 210 plus 8k greater than 0, taking 9 towards the other side. Simplifying this equation, at exactly at k margin, 210 equals to minus 8k. Therefore, k will be equal to minus 210 divided by 8. Therefore, k margin will be equal to minus 26.25 k margin. As k margin is negative, there is no intersection of root locus with the imaginary axis for positive value of k. Therefore, we can say that the entire root locus lies in the left half of the S-plane. Therefore, the system is stable. As we don't have any complex poles, there is no necessity for us to calculate for angle of departure as well as angle of arrival. Let us plot the complete root locus, the location of poles and zeros, and the region of root locus, as well as the centroid at -4 and the asymptotes at an angle of 90 degree and 270 degree. And we have a breakaway point exactly in this location, which has been justified in step number 5. And it is very clear that when making use of step number 1, P poles will be terminating at Z zeros. As we have 1 0, one of the pole out of the 3 poles will be terminating here. And the rest of the P minus 1, that is two poles will be terminating to infinity. One of the pole which is going to terminate at a 0 is nothing but a pole which is located at s is equal to -2. Exactly when k is equal to 0, its location is at k is equal to 0, and for the 0 at a location s is equal to -1, its exact location is in this position when k is equal to 0. And when k increases, this pole will be moving in this direction, and it reaches 0 exactly when k reaches infinity. And the rest of the p minus z poles, that is the rest of the two poles which is at -4 and -3, when k is equal to 0 will be in this location. When k increases, the location of these poles will be moving in this direction, and for -3 it will be moving in this direction, and they intersect with each other in this location that we call it as a location of multiple pole, which is nothing but the breakaway point. And exactly at this breakaway point, it breaks away, and based upon this location of the asymptotes, it will be terminating to infinity towards this direction. And this shows the final plot. Let me explain you the same plot making use of the MATLAB. The given open loop transfer function g of s is equal to k into s plus 1 divided by s plus 2 into s plus 3 into s plus 4. Simplifying further this expression, it will be of the form k into s plus 1 divided by s cube plus 9s square plus 26s plus 24. Therefore, let me take the numerator polynomial num equals to coefficient of s is 1 here, and we have a constant 1. Then the denominator polynomial, I can write it as s cube coefficient is 1, s square coefficient is 9, s coefficient is 26, and we have a constant 24. And then we know the command or a locus of num comma 10. This actually calculates and plots the root locus, and it returns the closed loop poles trajectories. And making use of this function, it is very clear that it is used to study the effect of varying feedback gain k on a closed loop pole location. Let us try using this in MATLAB. Let me click on this icon, MATLAB. In the command window, let me enter the numerator polynomial s plus 1. Then the denominator polynomial then equals to s cube coefficient is 1. Then it is 9s square. Therefore, s square coefficient is 9. Then 26s and a constant 24. Then let me type or locus of num comma 10. And now let us look at the plot. It is very clear that we have a 0 at s is equal to -1, and we have three poles, one at -2, one at -3, and the other at -4. And out of these three poles, one of the pole will be terminating at 0. Therefore, at k is equal to 0, the location of this pole is at -2. When k increases, there is a movement of these poles, and when k reaches infinite, it reaches the 0 here. Whereas on the other side, we have two adjacently placed poles. Therefore, there exists minimum one breakaway point as it is in the region of root locus. This pole exactly breaks away, and it is reaching infinity when k reaches infinity. As well as a pole which is located at -3, when k increases, it reaches exactly at the breakaway point at which multiple poles intersect with each other and breaks away, and it tries to reach infinity. Let us compare the MATLAB output with the plot which we have obtained. We have the location of poles and zeros and the region of root locus, the asymptotes, as well as the breakaway point. And we know that one of the pole will be terminating at 0. The pole at s is equal to minus 2 at k is equal to 0 terminate at 0 at s is equal to minus 1 when k reaches infinity. Whereas the rest of the two poles at s is equal to minus 4 and s is equal to minus 3, when k increases, there will be a movement of these poles in this direction and they intersect at a particular point which we call it as a breakaway point, and it breaks away and it try to reach infinity along the direction of the asymptotes. And this is a path which has been followed by this branches. And the angle of the breakaway point is given by 180 degree divided by a number of root locus. As we have 3 root locus in this case, 180 degree divided by 3, which will be equal to 60 degree. Therefore, the breakaway point takes an angle of 60 degree, and it will be following the direction of the asymptotes, which is clearly shown here in this MATLAB output. The angle at which it is taking as well as the path it tries to follow is the angle of asymptote at 90 degree as well as at 270 degree. Let me show you the complete sketch of the root locus and its direction of the branches. And this shows the complete sketch of the root locus. And we can try with any type of example problems making use of this MATLAB. It's a very simple command. And in one shot, you could able to see the output and you can cross verify with your answers. In the next lecture, let us solve few more example problems related to the construction of root locus. Thank you.